Hi, Jeremy. Glad you can join us today for the Stanford Blockchain Review. It's really great to have you here.
Absolutely. It's nice to have a chance to talk to you guys.
Yeah, for sure. Yeah, could you maybe first give us like kind of like a brief overview of what RISC-V does and what's kind of like the aim of like a ZKVM that you're building?
Yeah, absolutely. So RISC-V was sort of the inventors of sort of the first general purpose ZK VM that used an existing ISA. In particular, we picked the RISC-V ISA. This allows you to go from writing ZK via making custom circuits to writing ZK by using normal programming languages like Rust. And I think that this was a huge unlock for ZK development generally. And our sort of next phase of our company is really to go beyond just the sort of ZKVM, but really sort of address how do you actually use ZK in a blockchain context with our next product, Boundless. But I think this conversation is mostly focused on our existing ZKVM technology.
Yeah, that sounds great. So obviously you guys use the RISC-V architecture. So I'm curious on why did you guys choose this architecture as kind of like a baseline for proving programs in zero knowledge? Is it mainly like a performance concern or like a portability or reduced complexity? Have you guys considered other architectures in this design process?
Yeah, I think what really happened is, I was very interested in ZK. I kept trying to convince some of my developer friends to make use of it, but the sort of nature of writing circuits, people felt was like not like regular programming and very problematic. And then at some point, we came up with this idea of doing a VM and targeting compiling regular software into that VM. Once we did that, we looked at a lot of different architectures. We looked at, x86, ARM, WebAssembly, right? But basically, the goal was something that both uh, had an existing high quality compilers that targeted it. So something, that's supported by, LLVM and Rust and et cetera, as well as something which would be the most performant in a ZK context, right? And in ZK, the complexity of implementing a VM is actually quite high, and things like instruction decoding and extra ISA complexity really add up to a lot of performance issues on the ZK side. And RISC-V by far is the sort of simplest architecture. And additionally, RISC-V has a wonderful property that the base ISA is extremely small, and most of what would often be in a standard ISA is sort of as extensions. So, for example, floating point isn't required, right? So the other real consideration at the time was MIPS because there is pretty decent compiler support for that. But RISC-V is a slightly more modern. The fact that it's open also helped. But another reason is also the fact that RISC-V is already formally specified. And so
Mhm.
as we look into things like formal verification that the circuit constraints in fact match the ISA, that formal specification of RISC-V will come in very highly valuable. It will be very highly valuable. Additionally, it's also fully deterministic in a single-threaded execution model, which most ISAs are also not. So there's a number of different advantages. I think the choice was actually really quite clear once we did our research.
Yeah, that's super cool.
And you see
So
the industry has followed this as well. Like I think
Yeah, yeah,
most
it's great.
have also picked the same target for obvious
Yeah.
reasons.
definitely. Could you outline the design rationale behind your zero knowledge proof system? So, for example, why did you opt for Stark circuits and Graph 16 over alternatives like Planck or Marlin? And how do recursive or sequential proof components factor in? Do you employ any folding, in this case, witness folding techniques or other such schemes?
Yeah, so one of the reasons I got interested in ZK initially, I mean, I'd been following it for many years, but felt that it was not really at the level of being practical. But with the sort of, Stark paper by Eli Ben Sasson, I came to it became clear that the performance could be made to be sufficiently fast, given things like GPU accelerations and innovations like the use of sort of small fields. At the time the paper came out, small fields were not really in use. And I think that the other thing to really note is we did evaluate other options, But one of the nice properties about SNARKs is they're particularly efficient at repeated computation of like the same state transition function. And of course, with the ZKVM design, that state transition function is most of what's being done. And so that sort of architecturally really fit really well with it. And in terms of the Groth16 wrapper, really that's a much more pragmatic decision about minimizing the size of the final proofs and verification costs on Ethereum. Generally, we built most of the entire proof system using SNARKs, which have the advantages of being sort of post-quantum. But fundamentally, SNARKs are very hard to verify on existing blockchains. And so we provided that support for the sort of Groth16 wrapping for that. We looked at and we continue to look at new proof system innovations. We're actually, recently put together a deal with Irreducible to build a version of the ZKVM to run in the Binius proof system that they're building. But basically, our analysis is really looking at questions around how would adding support for this change to the proof system really add additional improvements, and how does that compare to other similar engineering efforts, right? Like in a lot of cases, for example, we looked at moving from Fry to Whir, but the reality is it was like a 20-30% increase in total end-to-end performance for proving, and there's still many much easier 20-30% improvements to be had just by additional engineering without really changes to those things. So I think as time goes on, we will continue to sort of stay on top of what the innovations are in the space. But yeah, so mostly practical reasons is the short answer.
I see. Now, building off of this, where in the future more people might be using these systems, do you foresee that you will update your current proof architecture? So maybe not even just like the types of proofs used, but the general architecture itself, such as the various proof systems, recursive structure, etc., where the scale of people participating in the blockchain space and therefore require the mass production zero knowledge proofs might be different, where you might need to accommodate 10x or 100x the magnitude of the number of proofs being generated. Because you just mentioned a 20 or 30% increase. Do you think that is sufficient in the future? Or do you think you'll need to leverage other technologies to be able to make that jump? Or what do you think? Yeah.
Yeah, so I think there's really sort of the short-term and long-term optimization opportunities, right? So I think like on the long-term side, like we are working with sort of both Binius or Irreducible on sort of binary field-based proof systems, and they're also working with Fabric in terms of hardware acceleration, both of which we think will give us a very significant increase. That said, I think we've been sustaining a 2 to 3x, sometimes 4x per quarter, improvements in performance optimizations because, and I think we're still quite a ways, a number of 2x's still before we reach sort of the end of just straight engineering performance optimizations. I think as an industry, a 10x over the course of the next year seems actually very feasible. And I think there's also and when I talk about these improvements, really there's actually sort of two different dimensions that matter. One of them is sort of this dimension of the cost per proof, which is really about the computational efficiency of generating proofs. And the other real one is around how do you distribute proving to minimize the total latency, right? Like I think one thing that's very interesting to everyone is being able to get real-time proving on Ethereum. And we're getting quite close. And my prediction is that well before the end of this calendar year, that we will achieve real-time proving for Ethereum blocks.
Wow, that sounds super cool. I'm also curious just in terms of like using SNARKs versus like SNARKs within the overall architecture, because I feel like a lot of the Ethereum community has coalesced around using SNARKs as kind of like a way to generate ZK proofs. So why did you guys like decide to stick with kind of like this original plan of using SNARKs within the system?
Yeah. I think really it just comes down to performance reasons. I mean, fundamentally for a VM where the sort of core constraints are sort of repeated as a state transition function, SNARKs just really are quite efficient. And additionally, I think most of the existing use of SNARKs either comes down to sort of the fact that Starks were a little newer, and for a while the development, and still to this day, actually, I think the sort of development tooling around Starks is weaker. Although interestingly, in our case, the end user doesn't need to deal with that developing tooling. That's really our sort of job as real experts. And then the end user just writes normal code. I think also, obviously the sort of ability to verify things efficiently with much smaller proofs and have good verifiers on Ethereum was also a real big challenge, right, with regard to Starks, which we solved sort of by this wrapping mechanism. But just in terms of from our measurements, sort of, it's still the most efficient way to do ZKVM kinds of computations. That said, we're not wed to any particular technological solution. If, next week I have some, benchmarks that indicate that switching to an entirely different proof system would be advantageous, we'll get started on it. From our perspective, the contract with our end user is really about the ability to run ordinary programs, from Rust inside of a ZK system. And so that provides, since that's sort of the way we're providing this capability to the user, that gives us a lot of room to make changes under the hood to follow the latest in sort of proof system research.
I see. Makes sense.
So it seems that RISC-V currently uses error constraints like an arithmetic intermediate representation to create a circuit. Have you considered using R1CS or CCS constraint systems? And what are the advantages of error constraints? And have you encountered any particular challenges using it? Basically, what was the rationale behind your constraint system?
Yeah, so I think error, interestingly, is actually fairly natural for things with a repeated structure, in the sense that the error has this notion of sort of looking at a column in some distance in the past, if you think of the rows as being sort of a time sequence, right? So it does have it is a little more natural in some sense. I mean, obviously R1CS is very general and you can do this kind of thing with that as well. But in terms of the repeated structure, it's not as self-evident. So CCS we also looked into when that came out. At this point, really mostly, we may have adopted that had that been the state of the art at the time when we first built the system. Interestingly, we are actually moving toward a new arithmetization scheme for what we're referring to as sort of the V3 version of the circuit. This is designed to support both Binius and our existing proof system, but it's basically using this sort of M3 architecture that was pioneered by the Irreducible team, which is sort of yet another way to sort of look at how to do arithmetization. We particularly like this M3 because it really provides for an excellent way to make the circuit more modular and to divide up the complexity of the arithmetization of something complex like a RISC-V circuit into a much more smaller pieces, and build sort of better software abstractions around it without really sort of limiting the performance of the proving, which of course, I mean, honestly, we'll do whatever it takes to get maximum performance, even if the software on our side is a lot of work. That said, I do think that M3 arithmetization offers some unique opportunities, and we're very excited about that sort of work on that we're doing right now.
Awesome. That's really cool. That's really cool. So is there a risk that extremely long execution traces could potentially compromise the security? So for example, making it easier for attackers to sample an invalid witness. And with your company in particular, do you encounter typical real world programs that could pose any issues here? And if so, how would you mitigate such risks? How would you handle a situation like this? Would you do updates to, if future programs become longer, to be able to handle invalid witness sampling? What is the analysis here?
Yeah, so it's an interesting question. I think that one thing to note is unlike some other sort of ZKVMs, one of the things we do is we divide the program up sort of into segments, which are proven separately. And so our security analysis is actually around the sort of per segment, and there's a actual hard limit on the per segment size. And so all of our security analysis, when we compute how many bits of security, is driven using this sort of maximal individual witness size. Now, what is interesting is that then we sort of combine these witnesses, which are each independent and proven completely separately. There's no sort of shared, you know, interaction between them. That said, we do use recursion on top of that, then to sort of combine them to prove the correctness of the entire execution, right? I think one thing that's interesting to note is I think there's been not as much analysis on sort of the sort of systemic uses of ZK in terms of, one way to look at it is if you think about when people talk about the security of, for example, a hash function, right? The security of a hash function is typically, written as a constant number, but the reality is, of course, if you run the same hash function many times, as the number of times you run it goes up, the effective security does drop, right? So I think in some sense, similarly to the way that we measure hash security in terms of what is the security of a single instantiation, I think there's some argument to be made that a similar model should be applied on the case of sort of long-running ZKVM programs. But that said, the sort of more straightforward concerns about sort of witness size don't really apply in our case because of the sort of segmentation mechanism that we use.
I see. No, that makes perfect sense. So how does your ZKVM interact with other cryptographic primitives like homomorphic encryption? Do you see zero-knowledge proofs as becoming essential for trustless execution of these protocols, or will they remain application-specific?
Yeah, so I think it's interesting. We certainly, there are some people who are actually combining FHE and ZK using our system, for example, running FHE computations inside of ZK so that to prevent and similarly, there's interesting interactions that people are working on sort of between the ZK and the MPC side. I mean, I think of course, most of these, some of these things are still unclear as to whether, specifically the MPC ZK stuff is really largely around like verifiable TLS and things like that. I think that you do get additional performance concerns and complexities, because each of these sort of systems incurs a significant overhead versus straight execution. And so exactly how practical some of these applications are still remains to be seen a little bit, although I think on the ZK, the TLS side, there's been some real significant improvements. I also think I think that you will start to see, though, more intermixing of these primitives. I think no one has really cracked the question of how to really provide all of the sort of properties that people want without very significant overhead. So we're really looking forward to sort of the research community's work on that. But yeah, so the short version is yes, there's some work being done. I have not been following all of the details of that in extreme detail. But there are some of our customers have been doing research on these matters.
Yeah.
Very interesting.
That sounds super cool. I'm curious on kind of like you mentioned kind of like there's this performance and like complexity overhead, especially with a lot of these newer systems. What does kind of the performance, what does kind of like the performance overhead look like just for like RISC-V system? If let's say I have a Rust program that I want to prove, how many times, what's kind of like the performance delay that I would want if I were using like RISC-V system there?
Yeah, so I mean, I think one way to look at it is sort of to measure what the sort of speed is in terms of sort of megahertz of execution in RISC-V, right? So you think about like a modern GPU could easily do more than 1 megahertz. I think we're at 2 point some for some of the GPUs. We're going to continue to get faster at that. And interestingly, by using parallelism and going across multiple GPUs, you can bring performance up to wherever the sort of emulation of RISC-V execution is. I think our current sort of what we call execution phase, it goes at about 60 megahertz right now. So if you think about that, that what you're really, this is not, these are numbers that would have been, in the early 90s, the sort of level of computing capability that people would have available to them. And so one way to sort of imagine the impact of ZK is that it sort of makes a modern GPU run about as fast as like, a 386 from the 90s, which is still reasonably fast, and you could do quite a number of interesting things with. In fact, a while back we actually did sort of ZK Doom, where we ran all of Doom inside of ZK, right? So I think the really another important thing to think about in terms of performance overhead is when you think about why you would use ZK, you're using it because you want to do verifiable compute. And blockchains are actually an alternative way to do verifiable compute, where you're using consensus and the fact that all of the validators have in fact double-checked all of the work in order to do verifiable compute. But of course, all of the validators need to re-execute that same logic, right? And at the end of the day, the Ethereum world computer is not really is slower than a Raspberry Pi, right? And in that regard, what's interesting is that from a cost perspective, because even though ZK has a fair amount of overhead, it only requires to be run once to generate a proof that can be then verified everywhere quite cheaply. The end result is that at this point, it's hundreds of times cheaper to prove something in ZK than it is to run the equivalent thing on Ethereum. We actually, in fact, can run using Steel, which is a mechanism by which we can run arbitrary smart contracts in the ZK VM. We can actually run a smart contract in RISC-0 for a much lower cost than ETH-L1 gas costs, right? So I think that it's just sort of worth considering that as ZK continues to reduce in cost, more and more of on-chain execution, which is really one way to do verifiable execution, is going to move to ZK, which is actually just going to be simply a more cost-effective way to do verifiable execution.
Yeah, I think that makes total sense. And I guess like as as hardware improves, as we get better ASICs and stuff, that cost is going to continue to go down as well.
Yeah.
So
I would argue, I would actually argue that in general, we're going to see probably a 10x reduction in cost over the course of this next year, maybe even more than that. And just from the existing sort of performance improvements that are already planned. And I think if you look on top of that on the possibilities of hardware acceleration, right? Like I think that the cost of ZK per sort of blockchain transaction, for example, at least for the blockchain use cases, is going to become so vanishingly small. I mean, at this point, it's less than a tenth of a cent per Ethereum transaction to prove the correctness of an Ethereum block. When that's 1/100th of a cent or 1/1000th of a cent, while the costs versus regular computing will still be significantly, verifiable computing will still be slower than regular computing, the effective costs will be so low relative to the use cases that costs will become not much of a topic of discussion.
Okay. So do you think that there's basically like this accelerated like Moore's law that's happening here with like ZK's like proving cost?
And eventually that will, I think, unlike Moore's law, which has run for quite a long time, I think that at some point the ZK acceleration curve will end up sort of matching Moore's law. But right now it's going significantly faster because, it's a new industry. The sort of improvements at the research level have been quite effective, but also we're seeing things like, just a lot of engineering improvements being made. We're also seeing things like hardware acceleration being contemplated. All of these will give us, much like ML initially, during the early days of deep neural networks, the effective acceleration in machine learning workflows was faster than Moore's law for quite some time, as the industry spent money to bring costs down very, very rapidly. And I think ZK is in a similar space right now.
Okay, that's super cool. So I guess like with this kind of like accelerating Moore's law, what do you think are some of like the key real world use cases for, let's say, RISC-0 ZKVM? Can you kind of like share some of your favorite applications or sectors that have been built using this thing that would not have been possible otherwise?
Yeah, I think I, I think let's break it down a little bit in terms of sort of blockchain use cases, and sort of other use cases. I think one thing to note is that, as I mentioned earlier, I think the idea that blockchain is really just a type of verifiable compute means that a lot of blockchain execution will move from on-chain to ZK for the cost reduction that is available. But I think additionally to that, we're going to start seeing much more rich applications being built on chain, because right now there's this very strong computational scarcity that exists on existing chains, because at the end of the day, there's only so much room in a block. There's only so much gas. And what that means is, as the demand for computation goes up on a particular chain, the supply remains fixed, and you get these massive increasing costs. And that means that lots of applications become not feasible because there just isn't enough compute available, or the compute becomes too expensive. And we sort of solve for this by, making L2s or rollups or what have you. But I think that at the end of the day, that just moves that sort of consensus bottleneck to a different location, and it creates all kinds of fragmentation. Whereas I think ZK has this capacity fundamentally to sort of unlock sort of an arbitrary amount of computing can be done and verified sort of succinctly. And what that means is that the costs of ZK computing are scalable. And as the demand goes up, people can bring more computing power online. And the cost per compute will never rise above, like, say, the cost of AWS on
Hmm.
demand. Otherwise, there's there's an arbitrage available in the
Yeah.
market, right? So as a result, we're going to see these much more interesting applications, right? Some of our customers, for example, on the DeFi side now can do full order books, or they can do, they can run Black Scholes like in like ZK, right? I think actually interestingly, you'll see these sort of cases like where Hashflow, for example, runs effectively what's a fully centralized exchange with the same sort of rates and UX that you would get from a centralized exchange, except by doing ZK verification, they can provide the same sort of security you get in the sort of on-chain use case, and prevent things like, FTX from happening, while still providing that sort of full, very wide, very powerful, use case. I think, obviously, there's a lot of things, like, I think, that will start to happen that have historically not been feasible. If you look at, say, even things like social networks, right? Like, the reality is that with gas costs being what they are, many of these applications that exist on Web 2 would be impossible to run in a Web 3 context. I mean, fundamentally, no one is going to pay, a $3 gas costs to, to like a post, right? And effectively, just that's sort of where things are. With the existing sort of limited limits that these systems have. But I would expect the richness of sort of Web3 applications to start moving toward what you see in Web 2, where, I think the sky is the limit. I also think there's a lot of really interesting privacy sort of use cases. I think that we are working toward adding support for client-side proving, which will, I think, enable a lot more of those to be, much more easily accessible. So I think the short version is, there's one way to look at it is, if you imagine that you could build trustless, decentralized applications and not have to suffer the sort of scarcity of compute that exists in the existing consensus-based systems, what could you build? And the answer is, like, vast. So yeah, I don't know. I don't know if that's maybe too general purpose, but hopefully that's helpful.
Yeah, yeah. I guess like both Yavor and I come from like developer background. So from kind of like the developer perspective, what does the tooling stack for RISC-0 look like? So how does, let's say, like a Stanford student go and explore this tooling stack and actually get started like building things using RISC-0's like ZKVM and proving system?
Yeah, I mean, I think you could, hop on by our GitHub or our sort of documentation page. There's a number of really good getting started guides. But I think the thing that's really startling to people is just how easy it really is, because literally if you already know how to write Rust code, you can write a ZK program that proves the correctness of anything you can write in Rust. And the amount of time to sort of make it run in ZK is like, a couple of minutes to get the thing set up, right? I think actually the interesting part is what that means is that actually the interesting questions become not how do you build your ZK circuit, or all these sort of low-level details, what field are you using, any of that kind of stuff. It really becomes about what's your application, what are you trying to prove, and whom are you trying to prove it to, and how does the sort of architectural flow around ZK is actually where the interesting parts become. I think one of the things to note too is that part of the reason we wanted to choose an existing ISA and have support for languages like Rust was not just because the language itself is easier to use, but because then you can pull in all of the sort of existing ecosystems work, right? Like if you want to prove, for example, some fact about a chess game in ZK, like, oh, there's a checkmate in 3 moves. I have a ZK proof that shows that. What's interesting is you could literally just import existing chess libraries in Rust, and the rules of chess are already there. You don't have to encode them at all. You're just reusing existing software that was made. And of course, that software wasn't made, um, you know, uh, specifically for ZK. It was just arbitrary software that encodes the rules of chess in Rust. But generally, almost many of these Rust crates become immediately usable in a ZK fashion. Maybe a couple of them that touch the operating system overly much don't run, since you're running effectively in an embedded environment. Although we are currently working on sort of mechanisms to support a lot of that, which are sort of on the next rev that we're building. At some point we're going to be able to run sort of GCC inside of ZK and prove the compilation of a Linux kernel, right? So it's only, I think one way to look at it is with RISC-V, you can really run anything you can write normal software for, you can run that in ZK. And it really isn't, it's like half a day and you'll be up and going. So
That's really wonderful. Yeah, final like quick question. What's kind of like what's kind of the things that you're looking to forward to most in the upcoming year?
yeah, so I think we've mostly been talking about the ZK VM in this conversation, but we're building Boundless, which is basically what we're calling a universal ZK protocol. And the goal is to bring the capacity to get ZK execution to every chain. So making it very easy for people to, on ETH-L1, go request a proof to be generated, have it land on ETH-L1, have it verified, have all the payment management happening, right? And not just on ETH-L1, but across every chain, basically bringing this, because if you look at it, ZK VMs make it easy to develop sort of ZK applications, but they still don't sort of fully simplify the process of how to integrate this sort of off-chain computing, this ZK verifiable computing, with sort of blockchain consensus-based, verifiable computing, and making that process both seamless while still maintaining the sort of full decentralization and censorship resistance of normal blockchain systems is actually an interesting, non-trivial problem. I mean, so that's one of the major sort of things our company is working on. On the ZKVM side, very excited about the sort of acceleration work that we're doing, with Irreducible and with Fabric, as well as a number of sort of internal, milestones we're working on as well. And then, yeah, I think we will also be providing additional support for a wider ecosystem of software to run inside the ZKVM. We have some announcements about that we'll be putting out eventually. So, keep an eye out. So I think there's a lot of exciting stuff going on. Yeah. So.
Sounds great. All right. Thank you so much, Jeremy, for joining us today.
Yep, absolutely. It was a wonderful time, and hope you guys have a great day. Bye.
Yeah, you too.